for putting together this wonderful conference in this beautiful city, in spite of food that was bad 2 years ago. So, anyway, the stuff I'm going to talk about today is joint work with my advisor, Martin Schmal. And I'm basically going to talk about two different dynamical systems. One is called the Panov plane, which is a generalization of an example due to Dmitri Panov that Martin and I both learned about a couple of years ago in Bonn from Josh and Ferran. And the other thing is the wind tree model. And what I want to do is I want to show how these two different examples are related to one another, and then also talk about a generalization of these generalizations of Panov planes that I'm going to discuss. So I think most of the people here coming into the conference already knew a lot of the background, so I'm not going to go over things very quickly. But just for the sake of completeness, let me just say that what I care about are billiards and polygons, and the way you study billiards and polygons, at least the rational polygons, is to associate a surface through the polygon called the unfolding of this billiard table, which is just a surface where geodesics on the surface correspond to billiard trajectories in that polygon. This unfolded surface is an example of something called a translation surface, which can be defined in a lot of different ways. One way is to say that it's just a countable collection of polygons glued together at their edges. And when you construct a surface like this, the surface comes with an atlas where all the chart changes are just translations. This is the translation surface. At least translations away from a discrete set of special points. This discrete set of special points comes from gluing vertices of these polygons together in such a way that the angle around one of these points after you do the gluings is greater than 2 pi. And in the case of translation surfaces, that cone angle will always be an integer multiple of 2 pi. A half translation surface is a generalization of a translation surface. It's defined in the same sort of way, except your chart changes can be composed with negations. So when you compose your chart changes with, or your translations can be composed with negations like this, your cone angles can now be multiples of pi instead of 2 pi. So in the case of translation surfaces, you have a well-defined notion of direction. You have this trivial linear holonomy on the surface. With half translation surfaces, you have almost trivial holonomy. So you can distinguish north from east on a half translation surface, but you can't distinguish north from south. The maps you care about on translation surfaces are affine diffeomorphisms, and these are just bijections that permute cone points and look locally like an affine map. So in this particular example, I have this L-shaped surface. I apply a shear to it, and then if you take this sheared L and you cut it along this dashed red line and rearrange the pieces, you get back your original L. So you have a bijection from the L to itself that locally just looks like an affine map. And since chart changes are just translations, possibly composed with negations, derivatives of maps are well defined. So regardless of what chart you compute the derivative in. In particular, for an affine map, this derivative is going to be a constant element of PSL2R, and the collection of all those derivatives forms the Beach group of the surface. And the reason we care about the Beach group is because of a famous theorem by Beach in 1989, where he said if this Beach group is really, really big, if it's a lattice, has finite covolume and PSL2R, then the geodesic flow in a fixed direction on the surface is either periodic or uniquely ergodic. So intuitively, these affine diffeomorphisms are like special types of symmetries on the surface. And what Beach's theorem says is that if your surface is really, really symmetric, so it has a really big group of symmetries, then geodesics have to be reasonably well behaved. Okay, so for what I'm going to do today, it'll be important to recall this classification of elements in PSL2R, where you say an element is elliptic if the square of its trace is less than 4, parabolic if the square of its trace is equal to 4, and hyperbolic if the square of the trace is greater than 4. So there are two particular types of maps that I care about. Those are the ones that have parabolic derivatives and the ones that have hyperbolic derivatives. So the ones that have parabolic derivatives come from having a cylinder decomposition of the surface and then twisting all the cylinders. So anytime you have a cylinder, a natural map to perform is a Dehn twist, which takes the cylinder and rotates it like a screw. So you fix the boundary curves of the cylinder, and you rotate by larger and larger amounts, starting from 0 going up to 2 pi as you move up the cylinder. And if you have a cylinder decomposition, and all the cylinders fit together in a nice way, so that this ratio of height to circumference are rational multiples of all your cylinders, then you have a globally defined affine map with a parabolic derivative. And the other maps I care about are pseudo-Anosovs. So in general, a pseudo-Anosov is a map that comes with two transversal foliations. So my fingers are like these, they're pointing in different directions. And in these two transversal foliations, or in one foliation, the map acts as a contraction, and the other foliation acts as an extension. In the case of these affine diffeomorphisms, this happens if and only if the map has a hyperbolic derivative.
Mm-hmm. Sorry.
Very much worried me for a second. So the first example, the first dynamical system I'm going to talk about is the generalization of this example. So Panov considers the complex plane with a certain half-translation structure, and he considers this particular example to solve an old problem of Anosov about constructing foliations with certain properties. And the way he gets that half-translation structure on the plane is he looks at the universal cover of a half-translation torus. So here you take your regular one-by-one translation torus and you glue this half-translation sphere onto it. So you still have a torus, but now it has a half-translation structure. So maybe I should clarify or say what these arrows mean. So these two arrows mean that I'm folding these two sides together. So this point here is identified with the point here. This point's identified with this point. This point's identified with this point. So I'm just folding those two sides together. So this has cone angle pi. This also has cone angle pi. When you look at the universal cover of this torus, you see the plane with these periodic slits. And because of the identification, when a geodesic enters one of these slits, it pops out on the other side, moving in the opposite direction. And the fact that these geodesics can change directions like this is what allows for interesting things to happen. So Panov will construct a pseudo-Anosov on this surface by combining Dehn twist in a certain way. So to talk about Dehn twist, you need cylinders. So the most natural cylinders, I guess, are the horizontal cylinder here, so this horizontal foliation, and this vertical foliation. These give you one cylinder in the horizontal direction and two cylinders in the vertical direction. So this may look like three cylinders here, but because of these identifications, I can take this cylinder, or this piece of the cylinder, and rotate it down to get a tall, skinny cylinder. And then what we'll do is we'll consider a twist, a single twist of that horizontal cylinder, and then a twist of the blue cylinder that's only a half twist of the red cylinder. So what's important about these two particular maps is the way they act in homology right here. And the reason that's important is that if you combine these maps in a certain way, you get a pseudo-Anosov whose action in homology is a 90-degree rotation. Okay? So since you have this 90-degree rotation in homology, if you raise this map to the fourth power, you have a pseudo-Anosov that's an element of the derivative that acts trivially in homology.
Mm-hmm.
And that 90-degree rotation, that sort of trivial thing in homology, is really important for proving this theorem of Panov's that if you look in the eigendirection of this pseudo-Anosov, then you have dense on the universal cover, so on this half-translation plane, the geodesics are dense on the plane. So to generalize Panov, I'm going to consider folded tori where I fold an L. And the reason I want to fold an L is because I want to relate these to the regular translation L's that people know a lot about. So I'm going to take this L-shaped polygon and I'm going to fold one or both of the legs of this L. Now the other sides are identified by translation like normal. So if I talk about a folded torus, this is what I mean. And then the universal cover of one of these things is what I'll call a Panov plane. So the universal cover, in the case of that folded L with both of the legs folded together, looks like this. It looks like the plane with these periodic rectangular obstacles where the edges are folded together. So that's a Panov plane. And you can generalize Panov's theorem to this more general type of Panov plane. The same idea carries over where if you have a pseudo-Anosov whose action homology is elliptic, then geodesics on the universal cover on the Panov plane will be dense. In geodesics and eigendirections of that pseudo-Anosov. So let me just show you a couple of pictures of this. So here is my Panov plane where I fold both legs of the L. And this geodesic starts right here, so just above this obstacle centered at 0, 0. This is the first 100 reflections of this trajectory. Here's the first 1,000, 10,000, and 100,000 pieces of the trajectory. So what's happening is that this trajectory is sort of slowly filling in the areas that it's visited before, while simultaneously moving further and further out, visiting more and more parts of the plane. Okay, cool. That took a long time, so I want you to see it. So there's sort of a naive similarity between those Panov planes and the wind tree models that we've been learning about all week, and that you have this sort of periodic obstacles in the plane. And what I want to do is see if there's any precise relationship between them, other than just they look the same. So just remember the wind tree model is this billiard table where you have these periodic obstacles at the last integer points in the plane, and you have a billiard that's bouncing around. Okay. So since we had these dense trajectories in the case of the Panov plane, and we had this thing that looked similar to this wind tree model, we wanted to know if the same trajectories for the same size obstacles and everything would be dense for the wind tree model. So we decided to test this idea with Sage. So we ran some experiments. So in the series of pictures I'm about to show you, the obstacles have the exact same size as the obstacles in the previous picture where we have this dense trajectory in the Panov plane. And the billiard starts in the same direction as that geodesic plane. So this is the first 10 reflections of the billiard in the corresponding wind tree model. So that was 10. This is 100, 1,000, 10,000, and 100,000 reflections. So we wanted to see something dense, and after we saw this picture, we kind of gave up on hoping this thing was dense. But we saw something much more interesting or unexpected for us instead. We saw this sort of escaping self-similar billiard trajectory. So we wanted to know what was going on. And one of the reasons this was really surprising for us was when we started doing this, these papers of Hubert, Lelivre, Trubetskoy, and then later Avila and Hubert had just come out showing that wind tree models are generally recurrent. They like to be recurrent. And here we have this thing that's escaping. So we wanted to know if we could explain this dichotomy of having dense trajectories in the Panov plane and for the exact same setup having escaping trajectories in the wind tree model. And more generally, can you use those Panov planes to study the dynamics of things in the wind tree? And you may ask why we would want to have this alternative way of studying things in the wind tree, and there are two answers to that question. One is that these Panov planes, since they're universal covers of tori, or just universal covers in general, they're simply connected. So topologically, they're much simpler objects than that infinite genus unfolding of the wind tree. And since they're universal covers, any map you have on the L, you can always pull back up to a map in this Panov plane. Okay. So I should say that shortly after we started doing this, Vincent put up a paper on the archive, which has now been published in the Journal of Modern Dynamics, this past year, where he also studies escaping billiard orbits in the wind tree model. And what Vincent's result says in particular is that for a certain collection of parameters, the set of escaping directions has Hausdorff dimension at least 1/2. So there's lots of escaping directions. Okay, so in order to relate these two things, I'm going to be talking about L-shaped surfaces a lot, and just to keep things straight, let me introduce a little bit of notation. So all of my L's are going to come from a 1x1 square, where I cut out an A by B rectangle from the top right-hand corner of that square. And if I want to fold a leg of this L-shaped thing, then I'll put a little hat over the corresponding parameter. So hat means fold.
Really, these one?
So, yeah, this is genus 1, and that's, of course, genus 2. Okay, so the precise relationship between these two surfaces that are covered by the wind tree model and the Panov plane respectively is that they share a common double cover. So this surface up here is actually the orientation cover of this half-translation L. So every half-translation surface has a canonically associated translation double cover. And here I've represented this double cover in 2 different ways. So let's say that you look at this one here. What I'm doing to get this picture is I'm cutting off this leg and sliding it to the left, cutting off the top leg and sliding it to the right. And the reason I'm doing that is to show that I have 2 different involutions on the surface that give me these 2 particular quotients. So here, if I take these 2 L's and slide them together, I get this surface. Here, if I take these 2 L's and rotate one on top of the other, I get this surface. And I guess I should say that this L is hyperelliptic. When you lift the hyperelliptic involution, you can lift the hyperelliptic involution up this double cover. When you take the quotient by that lifted involution, this is the surface you get. So this observation of this common double cover is really nice because it gives us a precise way to relate these half-translation L's to the normal translation L's, which are very well understood. In particular, this classification by Kalton-McMullen tells you exactly when those surfaces are going to be each. And so using that classification, we can construct half-translation L's that have this property that you have a pseudo-Anosov that's elliptically in homology by combining the twists in a particular way. Okay. So to construct a big family of surfaces that have this property of pseudo-Anosov that acts elliptically in homology, I want to look at surfaces where you only twist one of your cylinders when you do that big twist. So when I say a simple twist surface, what I'll mean is one of these half-translation L's where in either the horizontal or the vertical direction, when you perform a twist, you twist the longer cylinder exactly once. So the horizontal twists this purple cylinder exactly once, and the vertical twists this blue cylinder exactly once. So that's a simple twist surface. And so wanting a simple twist imposes certain conditions on the parameters on your A's and B's for these surfaces. And combining that with the conditions of Kalton-McMullen, you can say that a surface will be a simple twist surface if and only if its parameters satisfy these equations. Okay. So now here's maybe a really interesting thing. Maybe I shouldn't say maybe, it's a really interesting thing. So here's something that's really super interesting. So if you use these Panov planes, you can actually capture the dynamics of the wind tree billiard in kind of a neat way. So if you take this Panov plane where you only fold these horizontal legs of your L, and you look at a geodesic on this plane, and then the corresponding geodesic on the wind tree model, the y-coordinates of these 2 trajectories are always the same. And similarly, if you just fold the vertical sides of the L, when you look at a geodesic here and the corresponding billiard trajectory in the wind tree model, the y, or did I say that backwards last time? So here the x coordinates are always the same, and the other one, the y coordinates are always the same. So in Panov's paper, and the previous result I stated before, we looked at these pseudo-Anosovs who act elliptically in homology. But you could also act parabolically or hyperbolically in homology. So we'd like to know what happens in those cases as well. And so right now what we can say is that if you have one of these folded tori and you look at the Panov plane, if you have a pseudo-Anosov that acts hyperbolically in homology, then the geodesics on that universal cover on the Panov plane have bounded deviation. So what that means is that they stay confined to some rectangular strip of the plane. So let me show you a picture of that. So here's this Panov plane where both edges are folded together. And I'm looking at a geodesic in the eigendirection of some pseudo-Anosov whose action homology is hyperbolic. It stays confined to this little rectangular, infinite rectangular strip. So I should say that when you have one of these escaping trajectories that's constructed in this particular way, you actually get lots and lots and lots of them for free, because if you conjugate by elements of each group, you get another pseudo-Anosov that acts hyperbolically or elliptically or whatever on homology as well. So here's this original picture that we kind of call the snowflake picture that I showed you a little bit ago. And if I conjugate the pseudo-Anosov with, I think in this picture it's actually the hyperbolic or the horizontal twist, we get another direction, and that's what you see here. And this is conjugating with the horizontal twist twice, so the square of the horizontal twist. And then the product of the horizontal and vertical twists gives us yet another direction. So you get lots and lots and lots of these directions if you have one of them just by conjugating with these in each group. Okay. So the proofs of a lot of these properties rely heavily on the fact that this L that's covered by the wind tree is a hyperelliptic surface. So what we'd like to do is we'd like to generalize that just a little bit to say, okay, what if I'm not looking exactly at the L, if I'm looking at a different hyperbolic or hyperelliptic surface? Or what if I'm looking in general at a surface that just has some involution, not necessarily hyperelliptic? Can we apply the same sort of ideas to study surfaces in those particular cases? Okay. So let's say that we have a translation surface and it has an affine involution that's not an automorphism, it's not a translation. I'll call that an involutive surface. And to mimic that construction from earlier, where you took the regular translation L, you looked at a double cover, and then taking the quotient of some involution, you got a folded L. Can I repeat the same sort of process for other surfaces? So let's say I start off with one of these involutive surfaces. Can I find a cover that emits an involution that I can take the quotient of? So a conjugate involution. So I want to find all of the covers that have such a conjugate involution. In order to do that, I need to parameterize all of the double covers of this surface. So you can do that by looking at elements of the first homology group with Z2 coefficients. So normally you think about covers as being parameterized by subgroups of the fundamental group. But if you want normal covers, regular covers, then you can get away with just looking at homology. And what you do is you fix an element of, you fix one element of homology to plug into the intersection form. You let the other one vary. That gives you a map from H1 into Z2 in this case because double covers. The kernel of that is some normal subgroup of H1. And then you pull it back to pi 1, and that's a normal subgroup there, and that gives you. Okay. So these covers that you get by parameterizing things in homology will emit a conjugate involution if and only if the homology class you pick is invariant under the action in homology of the original involution. This forms a subspace of homology that I'll call H1 sigma, where sigma is my involution on the original surface. And it turns out that you can find a basis for this subspace where the representatives are simple closed curves, invariant under homology. Each one passes through exactly 2 fixed points, and no 2 pass through the same 2 fixed points. Or pass through, yeah, no 2 pass through the same 2 fixed points. So that observation about fixed points is kind of convenient because it gives you a really easy way to encode this particular subspace in homology by writing zeros and ones. Now, since I'm in Z mod 2, there's kind of an obvious, stupid way to encode things with zeros and ones. And what I'm doing, I claim, is not stupid. So basically, I'm ordering all of the fixed points, and then I'm putting a 1 if the corresponding simple closed curve invariant under the involution passes through that particular fixed point. So you can write down this particular subspace of Z mod 2 to some k plus 1. And that represents your subspace of double covers that have a conjugate involution.
Sorry.
Okay. So you actually have 2. If you have 1 conjugate involution, you actually have 2 involutions because you can compose with the Dehn transformation to get the other one. That's maybe not a completely trivial result because in general, if you compose 2 involutions, you don't necessarily get an involution. But in this particular case, it happens, and both the involutions are conjugate to your original one on the surface you started with. Okay. So, and the Dehn change transformation on that double cover actually descends to an involution on both of these surfaces. So these are quotients by your cover.
Sorry.
By your cover modulo those 2 different involutions. Those are these 2 things right here. And the Dehn change transformation descends to an involution on both of these. And sort of remarkably, if you take the quotient of those surfaces under that descended involution, you get back your original quotient from this surface modulo its involution. Okay, so you have this diamond diagram that relates all of these surfaces. Okay. So what I particularly care about are the quotients that are tori, though, because those tori are the things that have Panov planes as universal covers. So I want to count how many of those quotients are tori, and this is where that representing things with strings of 1s and 0s comes in really handy. It makes this into a really simple combinatorial problem. So you can calculate that there are this many tori associated to a surface with an involution using this construction. And in the special case of a hyperelliptic surface, so this has 2 in fixed points, so replace 2 in with 2g plus 2, and then you're looking for tori, so replace this thing. You can combine these with Pascal's identity to get this particular expression here. So if you have a hyperelliptic surface of genus G, you can associate 2g plus 2, choose 4 tori to it. And let me just give you a concrete example of that. So here I have the Swiss cross, which is really just the L-shaped surface, but I've cut off one of the legs, or not cut it off, but cut it in half. So cut a leg in half, move it to the bottom, cut this leg in half, move it to the right, and that gives you the Swiss cross surface. And the reason I'm representing the surface as the Swiss cross instead of as the L is just to make it very clear that there's this hyperelliptic involution that acts as a 180-degree rotation on this particular surface. And then the Weierstrass points of this involution are the points that are marked right here. And if you do this construction, where you try to construct all of these quotients that are tori, you get 15 different tori associated with this thing. 10 of them come from one of the involutions, 5 come from the other involution. Okay. So, there are a couple of obvious questions that arise from this. The first one is that I talked about things that act hyperbolically in homology and elliptically in homology. I didn't say anything about things that act parabolically in homology, and the reason is that we don't have any examples of pseudo-Anosovs, these L's, whose action homology is parabolic, and we also don't know a reason why they shouldn't exist, so we don't know what goes on right there. Another question is, can you use Panov planes to study other types of billiard systems in the wind tree model, and can you get more results about the wind tree by using these Panov plane constructions? And then finally, these elements that are elliptic in homology, you can think about them as being sort of like roots of things in the Torelli group. And as far as we know, people haven't really looked, I mean, a lot of people have looked at the Torelli group before, but as far as we know, people haven't looked at roots of things of the Torelli group before, presumably because they just didn't have a reason to. But now there's a reason to, because that says something about the dynamics in these Panov groups. Okay. So that's it. Thank you for your attention.
Questions?
Yeah, this is maybe a canonical question, but have you considered non-eigendirections in the Panov planes?
No, not yet.
Not yet. But do you have a gut feeling?
Not yet.
Not yet, okay.
So in one case you had, I sort of missed the example, but you had the orbit was found with a strip or something. What was that case? It was the.
That was when you have a pseudo-Anosov whose action homology is hyperbolic.
Okay.
Yeah.
Any other questions? Okay, let's thank Chris again.